In music, there is a concept called beats, and we will discuss this in our next, or in this lecture. So, if we have two tuning forks and we load one fork, one tine of the fork, let's say we put a plasticine or a rubber band on one of the tines, and then we strike the tuning fork, what would happen is we would have periodic changes in the sound intensity. And that would produce what we call beats. And you can see with this waveform here what a beat would look like. The two sound waves produced by the tines are slightly off from each other, and when they interfere with each other, we have these sort of beats, which are standing waves with waveforms, interference waveforms within them. So beats are formed by the superposition of two waves with slightly different frequencies. So this happens when we have waves with slightly different frequencies. You can copy this down, and if you can copy down that image, it would be helpful as well in your understanding. The frequency that's produced is called the beat frequency, and it's the number of beats per second. So for those standing wave beats that have alternating waves within them, each one of those loops is called a beat. And the beat frequency is equivalent to the absolute value of the difference between the two frequencies. So this is an equation. The beat frequency is equal to the absolute value of F1 minus F2, where F1 and F2 are the two frequencies. Note that when you're solving an absolute value, your beat will always be positive. So if your F1 is less than your F2, it will still be a positive, because whatever value we put in an absolute value, whether it's positive or negative, the output is always positive. This question says we have a tuning fork with a frequency of 256 Hertz, and it's sounded together with a note played on a piano. 9 beats are heard in 3 seconds. So what is the frequency of the piano note? Well, I'm going to show you how to do algebra with an absolute value because it's slightly different. Let's turn this camera on. So our F beat is equal to the absolute value of F1 minus F2. And our F beat, in this case, is equal to the number of beats per unit time. So let's substitute that and see what we get. We have 9 beats in 3 seconds. 9 divided by 3 is 3 hertz, or 3.0 hertz. That's our beat frequency. So let's substitute that into here and see what happens. So we have to, we now know that this beat frequency, this F1 minus F2, is 3 hertz. And we know one of these values is 256. And the other value is unknown. Well, to figure out one possible value, F1 is equal to, we essentially move the 256 to this side, and then we plus minus the 3.0. So F1 is equal to either 259 hertz or 253 hertz. And if we're not given any additional information, then that's our solution set with 2 possibilities. We don't have any way to solve that. We don't know which one is correct. So let's give a question here where we're given a little more information in the second part, so that we could possibly solve it. So our first case, we have a tuning fork with a frequency of 400 hertz is struck, and we have 20 beats in 5 seconds. So F beat is 20 over 5, which is 4 hertz. So that's our beat frequency. And we know F beat equals the absolute value of F1 minus F2. So that means that F1 minus F2 is equal to 4, and F1, or F2, is equal to, in order to put this over here, this would be F2 plus minus 4. So F1 equals 400 plus minus 4, and our possible values are 396 hertz or 404 hertz. This is how I show a solution set with squiggly brackets. That's my part A. Without being given any more information, that's as far as I can go. But in 2B, it says a third fork with a frequency of 410 is struck with the second fork above. And then we have 18 beats in 3 seconds. So we have a new F beat of 18 over 3. And that would be a 6 hertz beat frequency. So in this case, for this new fork, my F1 equals my F2 plus minus 6. And my F1 is my F2, which is 410, plus minus 6. So I have possibilities of 404 hertz or 416 hertz. And if this was, if this second fork was used in both cases, then the shared value between them is 404. So then you can write a therefore statement saying the F of the second fork is 404 hertz. Now we know for sure because we're given that additional information. This question says a 440 hertz tuning fork is sounded together with a guitar string, and we have a 3 hertz beat frequency heard. When an elastic band is wrapped tightly around one prong of the tuning fork, a new beat frequency of 2 hertz is heard. So for question 3, how could we solve this one? In this case, we are given the beat frequency directly of 3 hertz. So F beat equals F1 minus F2. And we can say F1 equals F2 plus minus F beat. And in the first case, when we have a 440 hertz tuning fork, we would plus minus 3 hertz. So our possible solutions are 437 and 443. In our second case, we would have an elastic band tightly wrapped around one prong of the tuning fork, and we have a beat frequency of 2. Well, actually, this is interesting because we don't need to do any calculation here. If we hear a beat frequency of 2 That means that wrapping something around would lower the frequency, so we would have to go to the lower value. So we can now just state, given this information, that F1 equals 437 hertz. And that's the same thing as our previous question. You notice that we had a higher beat frequency. So if we look at the work for our previous question, we ended up with a higher beat frequency than our first case, which was 4. So if we had a higher beat frequency, we could have just went and stated straight that this is 404. It would be the higher of the values. So that is our solution there, just by understanding the physics around it. How would a piano tuner use a tuning fork or a pitch pipe to tune a piano by adjusting the tension of the strings? They could sound the tuning fork and the piano string together and then increase or decrease the tension until fewer beats are heard. That would be how we would tune using a tuning fork.